Hi there, welcome back again to this course on ABE161. In the last video, we have already discussed the different types of structural loads, such as the dead loads, live loads, wind loads, roof line loads, and um, many more. In this video, we'll move on to the next section topic, which is the design philosophies. So basically, with all these structural loads that we have already discussed, then what if it, what if it acts on the structure in a combined way? So what if dead load, live load, and wind load acts simultaneously? So how do we manage those structural loads in the calculations? And also, we have to incorporate the safety factor in the calculations because we have already mentioned that in the design situations or let's say structural designs scenario, we there is always an uncertainties. So these uncertainties come from the loads, from the loadings, or let's say the materials itself. So for example, the strength of steel is um, the data, let's say, is it says 250 megapascal, or let's say 240 megapascals, but in reality it could be less than. So there are uncertainties, and we we take care of these uncertainties by including a factor of safety. Okay, so in this topic, we'll discuss the two methods and how to incorporate these safety factors, and then as well as um, in the scenario of combined loadings. Okay, so there are two common methods for determining the loads. So one is the ASD, or allowable strength design, and the other one is the LRFD. It's the load and resistance factor design. Okay, so in any method, the goal actually is um, that the allowable strength, or let's say the capacity, must be greater, let's say strength or capacity must be greater than the loadings. So that's the main, uh, actually, that's the main idea behind these two methods or approaches. Okay, so the allowable strength design is commonly referred to as the traditional method, whereas the LRFD is based on um, statistical statistical approach. Let's say statistical method. Okay, so for ASD, it says that if you put it in a mathematical expression, that's gonna be RA must be less than RN all over um, this factor. Okay, so this Rn is what we call as the nominal strength, and this one is called the required strength, and this one is what we call the safety factor. Okay, so basically this required strength, this is on the load side. Okay, so you can think of it as this is the load, then the nominal. Okay, whenever you see this nominal strength, then that's actually on the capacity, or let's say strength side. Okay, so in other words, like for example, you have this glass, let's say a glass, let's say it has a capacity of, let's say, capacity of 0 0.5 liters, for example. Okay, so as long as you are filling this, let's say you're filling this with, let's say with a water. So you're filling this as long as you're filling within this range, within this 0 0.5 liters, then that's gonna be safe. But if you're filling more than the capacity, then that's gonna be an overflow, right? So if you're within the capacity, then that's the safe, let's say safe region or safe status. But if you are filling it more than the capacity, then that's gonna be there's gonna be a overflow, and then the water's gonna spill out. Okay, so in that way, um, that's actually the failure of the material. So this capacity is the strength, whereas this required strength is actually on the load side. So that's the volume, the volume of the water in this glass. Okay, so we included a safety factor. So where do we get this value of safety factor? That's gonna be specified in the codes. So for example, you have a combination of dead load, live loads, and let's say earthquake loads. Then what's gonna be the safety factor? We'll be able to find it out in the code. So also the value of the safety factor depends on, let's say you have a dead load plus live load combinations, or let's say dead load plus let's say dead load, live load plus wind load, for example. Then that's gonna be there's gonna be a different safety factor. Okay, so that's the point of ASD. So the point here is it's just summing up all the loadings here. Okay, so dead load, live load, you just sum it up and then you apply the safety factor. Okay, so that's very direct, and actually that's the traditional way. Now for the LRFD, it's actually based on the statistical approaches. So the dead load, the live load, for example, they're not. I mean, the probability of occurrence of these dead load and live loads, they're not actually the same. So the LRFD, actually, if we put it in a mathematical expression, that's gonna be okay. So let's say what's this? Okay, so let's just say I forgot the Greek letter. This Greek letter. Let's just say this y. Okay, so y I and then q I. Okay, so must be less than the phi r n. Okay, so again, if we delineate this, this is gonna be the resistance side, or let's say the strength side or resistance side. Then this one on the left is the load side. Okay, so the Rn is the nominal strength, and this one, they're the loads. Okay, so let's say for example dead load, then live load, earthquake loads, etc. Okay, so these two, these the symbol here and then another symbol here, they're actually the something like the safety factors, but the term, technically the term is, this one is called the reduction factor, and this one is what we call the load factor. Okay, so you can see that it's actually there's compared to the AST, ESD is only one safety factors included in the calculation. Whereas the LRFD there, it has a let's say reduction factor for the resistance size because there are uncertainties in the resistance side. As I've mentioned, like for example, the specifications of the material, there are uncertainties. So, for example, we have an angle bore, let's say a 2 inches by 2 inches. Then we have a 316 thickness, right? So 2 inches, 2 inches. So the question is it gonna be exactly 2 inches, or is the thickness would be exactly 316? Uh, the reality is that there's gonna be some slight variations. So it's not gonna be that perfect, exactly 316, but probably close to it. So there are uncertainties here, and also uh, let's say the material strength. If there's a data, let's say a strength, a tensile strength of 250 megapascal, then probably the the real ones could be less than less than this stated value. Okay, so there are uncertainties, and also let's say if you construct a column, so let's say this is a cross section of a column, reinforced column, reinforced concrete column, then if you specify zero point 0.2 or let's say 0.3 meter by 0.3 meter width, in reality, when you construct that, it could be less than let's say 0.28. So that depends. Okay, it depends upon the accuracy of the construction. But the point here is, because of those uncertainties, then there must have some um, reduction factors. Okay, and many reasons as well. Later on, we'll discuss in our topic on reinforced concrete about these different values for reduction factors. Okay, for the load side, now the load sides we have the dead load, let's say the live loads. What else? Wind loads, etc. Okay, so these dead loads, there is also a factor, and this factor actually depends upon the combinations, the loading combinations. Let's say, for example, one common combination is the 1.2 dead plus 1.6 live. Okay, later on we'll discuss this, but for now let's just put it this way. So if you can see in this load combination, we have a 1.2 dead load plus 1.6 live load. Okay, so meaning that for the dead load we have a different load factor. For the live load we also have different factors. So just means that the dead loads, the probability of having a dead load is would be different than for the probabilities, or let's say uncertainties regarding this live load. So we have larger uncertainties here in the live loads because so meaning I mean okay, so let me refresh. We have this large value of load factors in live loads because we have larger uncertainties compared to the dead loads. Okay, so why? So for example, you have a beam. So a beam, if during the construction, let's say we have a 0.2 meter by 0.3 meter, sorry, 0.2 meter by 0.3 meter beam. So although during constructions we might have discrepancies in the values. I think that's the same as the ones I've discussed it here. So instead of zero point 0.2, of course in the drawing that's going to be 0.2, but in actual construction, then it might not be that accurate. So that could be, let's say, 0.19 or something. So that's why you have these factors and these dead loads. Okay, plus the let's see the data on the unit weight. Okay, so we if I remember it correctly, for the reinforced concrete, that's going to be 24 kilonewton per meter cube. Okay, so that's the unit weight of concrete. Okay, so but in reality, it could be different or slightly off or something. Okay, so that's why you have this 1.2. But you notice that we have less value than the live load simply because we have more control, or we can know more accurately, okay, compared to the live loads. We can determine the dead loads. If we have the let's say the dimensions, then we can determine the volume. Although there are uncertainties, we can still determine quite accurately as compared to the live loads. Okay, so for the live loads, now that's higher value. So meaning that, for example, if we design a a classroom, for example, so a classroom having some value of, let's say, I don't know what the value. I think 1.9 is the residential, 1.9 kilonewton per meter squared. Okay, so let's just take this value for example. So for a school, then although the classroom is designed for, let's say, 30 students, but in some situations it could be more than the design values. Okay, so probably instead of 30 students, it can go up to, let's say, 40, or uh, it depends. Or probably instead of just having some activities like soft activities, then probably there's going to be some movements, or let's say if there's an event, then there's going to be some party or something like that. So that could, the loadings could be more than that. Okay, so the point here is, because there's a larger uncertainties of live loads, then we have a larger value of these load factors. Okay, so this summation symbol, then this just mean that we have a load is, let's say, dead load, the summation of the dead loads and its load, the product of the dead loads and its load factors, then the live load and its load factors, then stuffs like that. Okay, so